Good day everyone, and welcome to where we are putting together solutions to those math and science areas that students are encountering at especially the CSEC or Form 5 levels and CAPE or 6th Form levels. In this video, we will be looking at CSEC Mathematics and in particular the topic of circle geometry. We will be looking at the solutions for past paper questions from May 2009 until May 2013. Feel free to like the video and add any comments down below so we can help you in whatever areas that you are getting problems with. Don't forget to look at the description down below where we have outlined the entire CSEC syllabus, all the past paper question solutions from May 2009 until the present. Let's review the major topics in CSEC Mathematics, of which there are 10 of them. And in this video, we'll be looking at number 8, Geometry and Trigonometry. This topic is tested as 8 questions in the multiple choice, 8 out of 60, and 21 marks out of the 100 in paper 2. This topic can be split into 2 parts, into trigonometry and geometry. Geometry itself can be subdivided into circle geometry, which is what this video is about, parallel lines or unknown angles, geometric construction, and transformation. This question was tested in all 5 years in our video from 2009 until 2013. Let's look at an overview of circle geometry. And there are some basic theorems that we are expected to know. So let's look at the first diagram. In that diagram, we have the 1, 2, 3, 4-sided shape, which is normally known as a dot. And it is formed from the dotted line, from the chord. So from the ends of the chord, we can see that they form an angle at the center and they form an angle at the circumference. And there's a relationship between the two of them. The angle subtended by a chord or made by a chord at the center is twice the angle subtended at the circumference. So if we have x at the circumference, then it's 2x at the center. Now notice one is inside the quadrilateral, inside the shape, and one is outside the shape, the angles. Now, if we take that and we open the legs out even further until it's a straight line, then it moves from being a quadrilateral into a 3-sided shape, a triangle. And the base will be the diameter. So now, if that's given us a straight line, that means 2x is equal to 180 degrees. And therefore, x, the angle of the circumference, will be half of that, which is 90 degrees. So what does that tell us? It tells us that if we have a diameter and we form a triangle from it, where of course all 3 vertices are touching the circumference, then this is always a right angle triangle. So it is developed from the dart rule. And if we open the legs even further, then it will go back to being, well, it will continue being, 2x at the center and x at the circumference. And of course, one angle will be inside the shape and one angle will be outside the shape. Let's look at the fourth diagram. There we can see we have a radius and it's touching a tangent. And what can we say? The tangent to a circle always forms a right angle, which is a 90-degree angle, with the radius. And in our fifth diagram, another radius, and we can see there it is cutting a chord in half, means that it is bisecting it. So when a radius of a circle bisects a chord, the 2 lines form a perpendicular, meaning they form a 90-degree angle between them. And if you go to the next diagram, we see a shape which has 1, 2, 3, 4 sides. So it's a quadrilateral. And all 4 corners lie on the circumference. So it's a special type of quadrilateral. It's called a cyclic quadrilateral. And what relationship can we find within all cyclic quadrilaterals? The opposite angles in a cyclic quadrilateral are supplementary, which means that they will add up to 180 degrees. And if we have two pairs of opposite angles, then we will get 180 plus 180, which will give us 360 degrees, which follows the rules of a quadrilateral as the total interior angles. We can also see that if we extend any one of the sides, then the exterior angle, which is formed by the outside of the cyclic quadrilateral and the side that was extended, is equal to the opposite interior angle. Now let's go to the 7th diagram. And from a chord again, we can see that the chord forms an angle on the circumference in 2 different places. And what is the relationship between them? The angle subtended by a chord is the same anywhere in that segment, in that part of the circle. In our next diagram, we have a triangle in which all 3 corners touch the circumference. And if we consider that there's a tangent which meets the circle at one of the corners, then there's a relationship in which we can say the exterior angle between a tangent to a circle and the triangle is equal to the opposite interior angle of the triangle. And in our final rule, we see that we have from a point, it forms 2 tangents. And we have the radius on both sides, 2 of them. And of course, from the rule earlier on, the 4th one, we know the angle between the radius and a tangent is 90 degrees. And we have 2 of those occurring. So we can see in a situation like this, that the tangents, the 2 of them formed from a point outside the circle, forms a quadrilateral that observes the same rules as a cyclic quadrilateral, which is that the opposite angles are supplementary. So they add up to 180 degrees. And let's look at the general steps that we should follow when we're solving this question. The first being that when you're doing a question, if students are getting problems, then they should make a sketch of these 8 theorems. And then identify which shape is relevant for what is being asked in the question. Redraw that shape, and then apply our rules and solve. May 2009, May 11A. The diagram below, not drawn to scale, shows a circle center O. Since it is not drawn to scale, it means that if we use our protractor to measure the angles on the diagram, it won't be correct, because this is just a sketch. The line DCE is a tangent to the circle. And let's recall, a tangent means a line touches the circle only at one point. And we can see in this diagram, it touches at point C. Angle ACE, the angle from A to C, and then C to E, the angle between those 2 lines, is 48 degrees. And the angle OCB, from O to C, and then C to B, is equal to 26 degrees. And both of these angles are shown on the diagram. Calculate the size of the angle, showing all steps in your calculations and giving reasons for your answers. Now this question has 6 parts. So the first part is asking us to calculate the angle ABC. If we look at the angle ABC, that is from the larger triangle. And there's a tangent involved as well. So if we look at our list of diagrams on the right hand side, or list of theorems, we can see that there are only two diagrams, the fourth one and the eighth one, which has a tangent involved. And which one of those has a triangle? It will be the eighth one. So let's extract that diagram. Let's bring it across. And since we have a triangle in there and we have the angle 48 degrees, the theorem says the exterior angle between a tangent to a circle and the triangle, and we could see that there, that's 48 degrees, is equal to the opposite interior angle of the triangle. And we can see, look how this has translated upwards. It slid upwards and rotated. So we can see the angle on the outside, on the exterior, is equal to the opposite interior angle. So what do we gather from that? That the angle ABC, which is on the interior opposite, is equal to the angle ACE, which is the angle on the exterior. Thus, angle ABC is equal to 48 degrees. And we solve the question. As we move on to part 2 of the question, let's include the 48 degrees that we just got for angle ABC in our diagram. So part 2 asks us to calculate angle AOC. And angle AOC, they didn't specify, but it is the smaller of the two angles. So let's extract our triangle. And let's recognize that if we're looking at AOC, which are two radii, then it will actually look like the first diagram in our list of rules on the right side. And we can apply the theorem. The angle subtended by a chord at the center, which is AOC, is twice the angle subtended at the circumference. So angle AOC, which is at the center, is equal to 2 times angle ABC. Remember, if we look at creating the angle AOC, we can say it started from 2 points. It started from A and C and went and met at O. Similarly, ABC angle started at A and C, the same 2 points, and went up and met at B. Thus, angle AOC is equal to 2 times 48 degrees, which is equal to 96 degrees. Part 3 of the question, let's also include the 48 degrees from part 1 and the 96 degrees from part 2. So part 3 is asking us to calculate angle BCD. So angle BCD, let's look at that, is the exterior angle between the triangle and the tangent. So if we want to calculate that there, and let's look at the rules on the right hand side. Out of the 9 pictures, 2 of them involve tangents. One of them is tangent with a triangle. If we know the opposite interior angle, which is the diagram 8, and diagram 4 involves the tangent with the radius of the circle. And if we look at that, we have a radius. OC is the radius. So let's extract the triangle. And if we extract it, we can see that the two angles OCB and angle BCD, those two angles form a 90 degrees, because OC is a radius and a radius forms 90 degrees with the tangent DCE. So if we know that and we know OCB, they gave us that, which is 26 degrees in the question, then we can substitute and solve. So 26 plus BCD is equal to 90 degrees. If we want BCD alone, we write back the 90 degrees, and what do we do with the 26 on the left hand side? We carry it across, we do the additive inverse, or we subtract, easier to see. So angle BCD is equal to 64 degrees. As in part 4 of our question, notice every time we find an angle, we write it onto our diagram. Part 1 we found 48, part 2 96, part 3 64. So now in part 4 of the diagram, they're asking us to calculate angle BAC. Angle BAC is part of the large triangle. Now, if it's difficult for us to recognize how we go about solving this question, then let's look at the list of rules on the right hand side for a large triangle. If we look at them, we have the second diagram has a triangle, but it passes through the center. And this triangle BAC does not pass through the center. So where else is there triangles? There are triangles in the 7 diagram and the 8 diagram. In the 7 diagram, two triangles share a chord, and this does not happen here. And in this 8 diagram, the diagram with the triangle and the tangent, right, that looks like what we have here. So let's extract that. And if we extract that, let's recall the rule. The theorem says that the exterior angle between a tangent to a circle and a triangle, which in this case is 64 degrees, is equal to the opposite interior angle of the triangle. So look how it slid across and rotated. So what we can tell is the interior opposite angle, angle BAC, is equal to the exterior angle of the triangle, BCD. Thus, BAC is equal to 64 degrees because we got 64 degrees for that angle BCD in the previous part. In part 5 of the question, they're asking us to calculate angle OAC, and that means the angle at A. So if we look at angle OAC, it fits into the smaller triangle. That smaller triangle already has an angle of 96 degrees, but we don't know the other two angles. But what can we recognize from that? We can recognize that OA, one side of that triangle, is the radius of the circle, and OC is also the radius of the circle. As such, let's extract the triangle and recognize that if two sides are the same, then this is called an isosceles triangle. And two angles are also the same. So let's write the angle at O plus the angle at C plus the angle at A. All three add up to 180 degrees. And the angle at A is the same as the angle at C. So let's replace that. So you have the angle at O plus the angle of C plus another angle of C, both of them of the same, will give us 180. And let's substitute what we know. We know angle of O is 96 degrees plus 2 angle of C is equal to 180. So if we want to get 2C alone on the left hand side, we need to move the 96 across. So we get 2C is equal to 180 minus 96. So 2C is equal to 84 degrees. And angle C now, we need to move the 2 across. The 2 is multiplying on the left hand side. When you carry it across, it will be the multiplicative inverse, or it means to divide. So 2 into 84, that gives us angle OCA, which is the angle at C, is equal to 42 degrees. Part 6 of the question, the last part, calculate angle OAB. So let's extract that out. And what do we recall? We recall that in part 4, we found out that angle BAC, the large angle here, is 64 degrees. And in part 5, we found angle OAC, which is 42 degrees. So what they're asking us to find, let's put a question mark there. Angle OAB. So angle OAB will be the large angle, angle BAC, minus angle OAC. Thus, if we substitute, we're going to get 64 degrees minus 42 degrees. So angle OAB is equal to 22 degrees. And now we've come to the end of the entire question. May 2010, number 10A. In the diagram below, not drawn to scale, PQ is a tangent to the circle PTSR, so that the angle RPQ is equal to 46 degrees and angle RQP is equal to 32 degrees. And if we look at our diagram, we can see both angles are given on the diagram. Calculate, giving a reason for each step of your answer in part 1, angle PTR. So if we look at the angle PTR, that is the angle inside the large triangle. and we know the angle 46 degrees on the outside of it between the exterior angle of the triangle and the tangent. So if we look at our rules on the right hand side, we can see in the 8th one that indicates the same scenario. So let's extract that part and see how it fits into our general theorems. So the exterior angle between a tangent to a circle and a triangle, and let's indicate that by having two black lines there forming the angle, the 46-degree angle. And let's recall, what about the theorem it says? It says that that is equal to the opposite interior angle of the triangle. So if we slide this 46 degrees down and then we rotate it, we recognize that it's the same angle, that they are equal. So the exterior angle is equal to the opposite interior angle. So we can write angle PTR is equal to angle RPQ. Thus, angle PTR is equal to 46 degrees. As we look at part 2 of the question, let's make sure we have our 46 degrees in at angle PTR, which we just solved in part 1. Maybe that will help us in part 2. So part 2 is asking us to do what? Calculate angle TPR, the angle at the top there. Now, there are a couple of ways to solve this, but let's first of all extract the entire triangle, the largest triangle there is, PTQ. And if we look at the largest triangle, what do we know about all triangles? That the total of all the interior angles of a triangle is 180 degrees. So let's consider that this large triangle, we know the angle there at T, we know the angle at Q, and the angle upon P at P is broken up into two parts. So let's write that. Angle PTQ, which is the angle at the middle letter T, plus the angle at Q, angle PQT, plus the angle up on top, which is broken up into QPR and TPR. So those angles will add up to 180 degrees. And let's substitute. 46 degrees plus 32 degrees plus 46 degrees, which we've worked out in part 1, plus angle TPR is equal to 180. And if we look at the line, there's only one unknown, so we should be able to solve this. So we can add up and we'll get 124 degrees plus angle TPR is equal to 180. And if we want to find angle TPR, we take the 124 on the left hand side and carry it across. It's adding on the left side, so when we carry it across, we'll do the additive inverse, which is subtraction. Thus, angle TPR is equal to 56 degrees. So let's make sure we have the angles 46 degrees and 56 degrees, which we found in part 1 and 2 in our diagram. And in part 3, calculate angle TSR. And where is that angle? That's the angle at the base of the four-sided figure, the quadrilateral. And if we look at our rules on the right-hand side, we can see our 6th diagram shows us the rules about cyclic quadrilaterals. So let's extract it and recall what's the theorem telling us. In a cyclic quadrilateral, the opposite angles are supplementary. And what does that mean? It means the angles TPR, the angle on top, and angle TSR, the angle at the base, will add up to 180 degrees. And we know the angle on top, so we can substitute 56 degrees plus angle TSR is equal to 180. So if I want angle TSR, we carry the 56 across. It's adding on the left hand side, so it will be the additive inverse or subtract on the right hand side. So it will be 180 minus 56 degrees. Thus, we've solved our question. Angle TSR is equal to 124 degrees. In May 2011, number 10A, In the diagram below, not drawn to scale, W, X, Y, and Z are points on the circumference of a circle, center O. T, Y, V is a tangent to the circle at Y. Angle XWV is equal to 64 degrees and angle ZYV equal to 23 degrees. Calculate, giving reasons for your answer, the measure of the following angles. So if we look at the question, we can see that all the information that was written was given in the diagram. So now let's look at what part 1 is asking us for. Calculate angle XYZ. So if we look at angle XYZ, we can recognize that it is the base angle in the four-sided figure, in the cyclic quadrilateral. So if we look at our sixth diagram in our theorems or diagrams on the right hand side, we can see the cyclic quadrilateral, and let's recall that means that it has four sides and all four corners touch the circumference of the circle. So let's extract that cyclic quadrilateral and let's recall what is the theorem. The theorem for cyclic quadrilateral says the opposite angles in a cyclic quadrilateral are supplementary. And what does that mean? It means that if we look at the angle on top, XWZ, the angle at W, plus XYZ, the angle at Y, that will be equal to 180 degrees. And we can substitute XWZ, the angle on top, is 64 degrees, plus XYZ, which is what we want to find, is equal to 180 degrees. And if we want to find XYZ, we need to move the 64 across. The 64 is adding, so when we carry it across, it will do the additive inverse. So it will be 180 degrees minus 64 degrees. As such, XYZ, the angle at the base, is equal to 116 degrees. In part 2 of the question, they're asking us to calculate angle YXZ. And if we take a look at that angle, that YXZ is part of a triangle. And what do we know? We know the angle on the outside or the exterior of that triangle and the tangent. So if we look at our rules on the right hand side, if we look at a triangle with a tangent involved, that will be our 8th diagram. So let's extract it. And when we look at it, let's recall the theorem. The theorem states the exterior angle between a tangent to a circle and a triangle, and let's put that up there with two black lines to show the angle, which we know, that is equal to the opposite interior angle of the triangle. So if we slide this across and we rotate it, we can see that they're the same. So angle YXZ is equal to angle VYZ. Thus, angle YXZ is equal to 23 degrees because that is given in the diagram. Now for the last part of the question, calculate angle OXZ. So we need to find the angle, that small angle in that triangle, and we don't have any other angles in that as yet. So let's do some working first. We do know the angle up on top, which is W, the angle at W, which is 64 degrees. And if we look at that, and we look at our diagrams on the right hand side, our first diagram looks similar to this. So let's apply that. So let's extract the triangle. Sorry, it's not a triangle, it's a four-sided figure. Let's extract that quadrilateral. And let's recall the theorem. The angle subtended by a chord, and in this case the chord is XC, at the center. So that's that angle XOZ is what they're talking about. So the angle made at this point is twice the angle subtended at the circumference, up on top at W. Because at W, it came from the same chord X and Z went and met at W. Just as X and Z, those lines produced O. So angle XOZ, the angle at the center, is equal to 2 times the angle at the circumference, angle XWZ. And we can substitute because we know the angle on top at W, which is 2 times 64 degrees. So angle XOZ is equal to 128 degrees. Now this helps us, but isn't our final answer. So let's extract the small triangle now, XOZ. And we see the 128 degrees there. And what do we know about the triangle? Triangle O. In that triangle, OX is equal to the radius of the circle, and OZ is also equal to the radius of the circle. As such, both sides are the same. So we can now recall that the triangle OXZ is an isosceles triangle. And if it's an isosceles triangle, the angles at X, which is OXZ, and the angle at Z, which is OZX, both those angles are the same. Now, we know the angle at O, and let's recall that the total internal angle of a triangle, when we add up all the angles, will give us 180 degrees. So we can now write the angle OXZ, which is the angle at X, plus the angle at Z, plus the angle at O, all three is equal to 180 degrees. And two of them are the same, so we can write 2 times OXZ plus the angle at O is equal to 180 degrees. And we know the angle up on top, so we can substitute that. So 2 times X, or OXZ, plus 128 degrees is equal to 180 degrees. And if we want to find OXZ, we can carry the 128 across, it will subtract. So we'll get 180 minus 128. So 2 times X will give us 52. So if we want X, or angle OXZ, it'll be 52 divided by 2, which is 26 degrees. And as such, we've completed the question. May 2012, number 10B. The diagram below, not drawn to scale, shows a circle center O. The line UVW is a tangent to the circle, which means that line touches the circle at only one point. And we can tell from the diagram that point is U. ZOXW is a straight line, and we can see it's passing through the center of the circle. And angle UOX is equal to 70 degrees. Part 1. Calculate, showing working where necessary, the measure of angle A, angle OUZ. Now if we take a look at that triangle, we don't have any angles inside of it. So let's see if we could find one of those. Since we know the 70 degrees is given to us from the diagram, we should be able to find out the angle on the left of it, angle ZOU. Because when you add those two angles, they give you a straight line. So let's extract the center with the two lines crossing showing the intersection. And what can we say? Those two angles, ZOU and XOU, are supplementary. So let's write that. ZOU plus angle XOU is equal to 180 degrees. And we can substitute. So ZOU plus 70 degrees is equal to 180. ZOU is equal to 180, carry the 70 across. And ZOU is equal to 110 degrees. So we now have an angle inside of the triangle. Let's extract the triangle. And as we take a look at it now, what do we recall? We can say that OZ is a radius of the circle. OU is also a radius of the circle. Since we have two sides which are the same, then this triangle is an isosceles triangle. Let's recall the interior angles in a triangle are supplementary. So, and this is an isosceles triangle, so we can write that angle OUZ plus angle OZU plus angle ZOU is equal to 180 degrees. Since some of my students get problems with this, we can shorten it by picking the middle letter. So angle U plus angle Z plus angle O is equal to 180 degrees. And we know two of them are the same. We know that angle U and angle Z are the same. So we can say angle U plus angle U, or we can write it as 2 times angle U plus, and what is angle O? We worked that out before, 110 degrees is equal to 180. So we can carry the 110 across, so we get 2 times angle U is equal to 180 minus 110, and that will give us 70 degrees. So if we want angle U or angle OUZ, that's the full name, then that will be 70 degrees divided by 2, which is 35 degrees. So we've solved this part of the question. Part B of the question asks us to calculate angle UVY. So let's recall that in the triangle UVY, or even the smaller triangle UXY, we don't have any of the angles there. However, we have a chord UX, and from that chord, it forms a triangle at the center, O. And from the same chord UX, it forms a triangle at the circumference at Y. So this is similar to the first rule on the right-hand side, where we're showing it with the blue arrow. And let's extract it so you can see it better. And similarly, if you're doing the question in the examination, then if you're getting problems, we draw that part of a diagram that's required for you to make life simpler, so you can figure out what's happening. So the theorem says the angle subtended by a chord at the center, which is at the point UOX, and we have that, is twice the angle subtended at the circumference at UYX. So we can write that angle UYX is equal to angle UOX divided by 2, because it's half the amount. And that would be equal to 70 degrees divided by 2. Thus, angle UYX is equal to 35 degrees. Now let's take a minute and see how that helps us. So let's recognize that if we look at the big triangle UVY, then UV, that line, is a tangent to the circle. And the line UY passes through the center. So we have a rule for that. If we look at the diagrams on the right hand side, the fourth one shows us that the angle between the radius or the diameter and a tangent is 90 degrees. So let's extract that. And when we extract it, we recognize a couple things. One, the angle between UY and UV is 90 degrees. And we have the angle up on top, UYV, because it's the same thing as angle UYX as we worked out before, to be 35 degrees. So let's recall the theorem, the tangent to a circle and its diameter are perpendicular. So if we substitute there, remember all three angles will add up to be 180 degrees inside a triangle. So angle UYV, the one on the circumference up on top, plus angle YUV, which is at the base, and angle UVY is equal to 180 degrees. And remember, we want to work out angle UVY, which means we're supposed to have the other two. So let's substitute. 35 degrees plus 90 degrees plus angle UVY is equal to 180 degrees. And we can work out that. 35 plus 90 is 125 degrees. Plus angle UVY is equal to 180 degrees. So if you want angle UVY, we can carry the 125 across. And 180 degrees minus 125 degrees gives us our answer that angle UVY is equal to 55 degrees. So we solved the second part of the question. Let's look at part C of the question, which is asking us to calculate angle UWO. And if you look at the diagram, that angle is where the diameter, which was extended, meets the tangent. So if we form a triangle, let's say we form triangle UWO, let's extract it and see what we have. Now this comes back to the same fourth rule in our diagrams on the right hand side, showing us the angle between the radius or diameter, which is OU in this case, and the tangent, which is UW, forms a 90 degrees. So recognizing this, and we call the interior angles of a triangle are supplementary, meaning that all three angles will add up to 180. Then let's write it. Angle UOW, the angle at the center of the circle, plus angle OUW, the angle at the tangent, plus angle UWO, which is what we want to find, is equal to 180 degrees. And let's substitute. 70 degrees plus 90 degrees plus angle UWO is equal to 180 degrees. And if you look at this entire line, there's only one unknown. So we should be able to solve. So 70 plus 90 is equal to 160 degrees plus angle UWO is equal to 180 degrees. As such, angle UWO is equal to 180 minus 160, and that gives us 20 degrees. For part 2 of the question, name the triangle in the diagram which is congruent to triangle ZOU. So let's recall the conditions of congruence between two triangles are they must have the same shape and the same size. Or we can say it a little differently, that all three angles must be the same and all three sides must be the same. So if we're checking two triangles, then the congruency properties we're looking for, we don't need to look for all 6 things. We need to look for at least one side to be the same length in both of them and 2 angles. Or 2 sides are the same and 1 angle is the same. Or all 3 sides are the same in both triangles. What about if all 3 angles are the same? If all 3 angles are the same in 2 triangles, it could be that one triangle is an enlargement of the other triangle. And in that case, the size will not be the same. So we would say that those triangles are similar in that particular situation. So let's extract ZOU, that triangle. And what do we recognize from there? It has 2 radii, OZ and OU. And the internal angle at O is 110 degrees. We worked that out in part 1 of the question. So, which triangle has 2 radii and 110 degrees at the center? That will be the triangle in yellow, the triangle OXY. So we can say that triangle ZOU is congruent to triangle OXY. Now there's a part B of the question, the last part of this, which is asking us to do the same thing for triangle YXU. So let's extract it and look at triangle YXU. What do we know? We know YU is a diameter. And if we have to get a triangle that's congruent to it, that will also need to have a diameter, the same length. And it has a chord UX. And let's recall from looking on the right hand side on the 7th diagram, if there's a chord which produces an angle on the circumference, wherever it produces it, it's going to be the same angle. So if we use UX as a chord, the angle formed from UX at the point Y we worked out to be 35 degrees, will be the same if we use ux forming the angle at z. So let's see. This triangle we have in blue in yellow has a diameter and a chord ux and an angle of 35 degrees. And if we look at the triangle now in blue, it has a diameter zx, it has the same chord ux, so the two sides are the same, and it shares an angle of 35 degrees at the point z. So that is like SE, two sides and an angle is the same. As such, triangle YXU is congruent to triangle ZUX. And we've now completed this question. May 2013, number 10A, part 1. The diagram below, not drawn to scale, shows a circle, center O. EBC is a tangent to the circle. That indicates that the straight line touches the circle at one point, at the point B. Angle OBA is equal to 40 degrees, which is identified on the triangle, and angle OBF is equal to 35 degrees, which is also identified in the triangle. Sometimes questions are given where the information is written up on top, but it is not put into the triangle or the diagram that's given. In this case, it is. So calculate, giving reasons for your answers, the measure of EBF, that angle. So let's extract it. And if we look at the fact that EBF, that angle, uses the line EB. EB is a tangent to the circle. And we look at the list of rules on the right-hand side, the diagrams, to help us. Then we see the fourth diagram has a tangent making a perpendicular or 90-degree angle with the radius. And that's the same situation here. So we can see that the angle between a tangent to a circle and the radius is perpendicular. Thus, angle OBF and angle EBF are complementary. So angle OBF plus angle EBF, those two angles, when you add them up, it'll give us 90 degrees. And we know one of them, so we can substitute. 35 degrees plus angle EBF is equal to 90 degrees. And if we want angle EBF, then we can carry the 35 across from the left-hand side. It's adding, so when you carry it across, you'll do the inverse of adding or addition, and that will be subtraction. So 90 minus 35, the angle is 55 degrees. And that's the angle on the outside of the triangle, between the triangle and the tangent. As we look at part 2 of the question, let's remember that anytime we find an angle, we solve it. Let's put it into the question on the diagram itself. So let's put in the 55 degrees from part 1. So part 2 is asking us to calculate angle BOA. So if we look at the angle BOA, it's the minor angle, the smaller one. And let's extract that triangle. And if we extract that triangle, what do we recognize? We recognize that OB and OA are radii or two radiuses of the circle, which means that if two sides of the triangle are the same, then triangle OBA is an isosceles triangle, which means what? It means that two angles are the same. So let's recall that if we add up all the angles, angle OBA plus angle OAB, the one at A, plus angle BOA, the one at the center, that will equal to 180 degrees, because all the angles and the interior angles in a triangle will add up to 180. And we can substitute. We know two of the angles are the same. One is 40 degrees on the left-hand side and one is 40 degrees on the right-hand side. So 40 degrees plus 40 degrees plus angle BOA is equal to 180. And 40 plus 40 is equal to 80 degrees. So 80 degrees plus angle BOA is equal to 180 degrees. We have one unknown in the line we just wrote, so we should be able to solve it. So angle BOA is equal to 180 degrees. And let's move the 80 from the left-hand side to the right-hand side. So it will subtract. So angle BOA would be equal to 100 degrees. That's the angle at the center. Let's now look at part 3 of the question, where it asks us to calculate angle AFB. Angle AFB means the angle at F, and it started at the points A and B. So let's extract that. And if we look at the chord AB, which we have as a dotted line, from A and B, from those 2 points, they went together and met at F. So that looks like, if we look at our diagrams on the right hand side, our rules where we have shortened it by drawing little diagrams instead of having words, then the shortest one, the point that it'll look like will be the first diagram. So the theorem says the angle subtended at the center from a chord. So if we look at the chord AB, it came together and met at O. That's the center of the circle. And we know the angle there. So that angle is twice the angle subtended at the circumference, which is where it met at F. So angle AFB is equal to half angle BOA. And we know angle BOA, so we can substitute that. So angle AFB is equal to 100 degrees divided by 2. Angle AFB is equal to 50 degrees. In part 4 of the question, we're asking to calculate angle OAF. Now let's recall that in circle geometry, there are usually many different ways to solve each angle. So I've tried to choose what I thought was the simplest way for my students. So if we extract the triangle, because the angle deals with ABF, then what do we recognize? We know that the interior angles of a triangle are supplementary, meaning the angle at B plus the angle at F plus the angle at A will be equal to 180 degrees. But if we look at our diagram, yes, we have those 3 angles, but those 3 angles are broken up in a couple parts. So the angle at B is really the angle OBF plus OBA. And the angle at F we know is AFB, which we found as well. We know all 3 angles. And the angle at A can be broken up into 2 parts. The angle OAB, which we know because that's part of the isosceles triangle. And angle OAF, which is what we want to find. So we have 1, 2, 3, 4, 5 angles. When we add them up, will give us 180 degrees. And out of those 5, we know 4 of them. So there's only 1 unknown, so we can substitute and solve this question. So let's substitute. Angle OBF is 35 degrees plus angle OBA is equal to 40 degrees. Angle AFB, those 2 were given before in the diagram originally. Angle AFB we worked out to be 50 degrees. And angle OAB was part of the isosceles, was 40 degrees. Plus angle OAF is equal to 180 degrees. And if we add up those 4 angles, it will give us 165 degrees plus angle OAF is equal to 180 degrees. So if you want to find angle OAF, let's move the 165 from the left-hand side, where it is adding, and carry it across to the right-hand side, where it will do the additive inverse, or easier to say, to subtract. So 180 degrees minus 165 degrees means that angle OAF is equal to 15 degrees. And we've now solved the question. We've now come to the end of CSEC past paper questions in the topic circle geometry. This video dealt with past paper questions from 2009 until 2013, these 5 years. And our next video will deal with questions from 2014 until 2018. Don't forget to look at the description down below so you can get an overview of how we've broken up the entire CSEC Maths syllabus and the order in which we suggest that you look at the videos so you get a better grasp of the content and therefore be able to increase your grade.